Hello, my name is Paul Morges. I am a second-year master's student at CPES. I received my Bachelor's of Science in Electrical Engineering from Virginia Tech. My advisor is Dr. Burgos, and my research interests are in active gate drivers for wide bandgap semiconductors. Today I'll be speaking about voltage-controlled gate driver technology with a focus on controlling drain current and drain voltage transients.
Hello, my name is Paul Morges. This is a presentation on variable voltage active gate drivers to reduce drain source overshoot and control drain current rate of change. This work is sponsored by the Wide Bandgap Fellowship through the U.S. Department of Energy. Silicon carbide MOSFETs are becoming increasingly popular in power electronic systems, such as powertrains for electric vehicles and inverters for renewable energy. This is because silicon carbide, when compared to silicon, can handle higher temperatures, higher operating voltages, and switch faster. This high switching speed leads to smaller filter components such as inductors and capacitors, which heavily contribute to the weight of an inverter or other power electronic system. The drawback of this higher switching is caused by the internal parasitics of the device, mainly the capacitance and inductance, which during rapid switching will cause significant overshoot and oscillation for both turn on and turn off. This overshoot is undesirable because it causes the devices to be derated so the overshoot does not exceed the maximum rating of the device. Also, with a high switching frequency, the DI/dt increases, leading to more EMI being generated. This means that additional EMI shielding or mitigation techniques must be used, and this can lead to a larger, more expensive system. There are many methods of handling the previous mentioned drawbacks from high switching speed. The image here of a simplified switching circuit which has a single MOSFET. There are two methods of mitigating the negative impacts from switching frequency that can be commonly used. The first is a gate resistor shown here in the green circle, which acts to reduce the drain current during turn on and turn off. This lowers the DI/dt and also reduces the rating on the drain of the device. However, as you increase the gate resistance, you'll see higher switching losses. The second method is a snubber circuit shown here in red, which shunts the high frequency oscillations to the ground, thus limiting the overshoot and ringing, but increasing the power loss during switching. This is why my research has three targets. Target 1 is to reduce the voltage overshoot and undershoot from a underdamped to more of a critically damped response, as you can see here. Second is to create a flexible system that can be adapted to operate many different devices and be tuned to meet various performance requirements. And the third is to control the drain current rate of change as a way to reduce EMI generated during switching. At its fundamentals, a gate driver is simply a way of controlling the conduction of a power semiconductor, for instance, a silicon carbide MOSFET. This is done by driving the gate source voltage above a specific threshold, which enables the device to start conducting and become almost a short circuit. To turn off the power device, the gate source voltage is reduced below that conduction threshold, which then causes the device to behave like an open circuit. The system on the left shows a simplified gate driver using a push-pull circuit, which based on a control signal A5 or A6 will either connect a 22-volt source to the gate resistor, thus turning the device on, or connect the gate resistor to a negative 5-volt source, turning the MOSFET off. The arrows here and here show the flow of current for each state. With this system, there is only a high or low applied voltage limiting the performance, as the only method of control would be the gate resistor, which is static during operation, as you cannot change it during the system's operation. You can see down here the VGS voltage waveform, which goes from a low to a high with no transition between. With the proposed solution to the right here, the same push-pull concept as the conventional circuit is used. However, there are now numerous positive voltage connections that can be made. This provides two benefits. The first is a slower increase of the gate source voltage from its low value to a high value, which you can see here from -5 to 10 to 15 to 22. The second benefit is the duration of each of these voltage connections can be changed dynamically, allowing for switching performance to be tuned to meet desired system performance. So this duration here for 10, 15 volts can be changed on the go or in advance of the circuit operation. Looking at the simulation results when comparing the conventional versus the proposed driver, this simulation was conducted using a drain current of 40 amps, a bus voltage of 800 volts, a gate resistance of 2 ohms, and a Cree silicon carbide MOSFET. First, looking at the drain source voltage for turn on, you can note that the red is the conventional voltage from the conventional gate driver, and the blue is from the proposed gate driver. When we look at this lowest point, you might notice that the conventional driver has an undershoot of almost 42 volts, whereas the proposed is reduced down to almost about 2 volts. This shows a significant reduction in the drain source voltage undershoot during turn on. Next, looking at the turn on drain current, you can note that the conventional driver has a very high DIDT as it goes from low to high in a very short period of time, whereas the proposed system has a much lower DIDT, which means it would generate a lower EMI. Final thing to notice is the applied voltage to the gate resistor. The red again is showing the conventional driver, which just goes from low to high, and the blue shows the proposed driver using 10 nanosecond pulse durations. So you can see a 10 volt, a 15 volt, and then a 22 volt connection being made. It is important to note that the duration of these pulses can be changed, and so this blue waveform can be tuned to have a higher or even lower DIDT based off of what is needed for the specific system. The actual hardware realization of this is relatively straightforward. To control the system, a high-speed FPGA is used, which will generate the necessary control signals. This then is used to drive a LiDAR-based gate driver, which accepts very narrow input pulses and provides an isolation barrier from the FPGA to the power system. This LiDAR gate driver then drives the individual GaN high-speed MOSFETs, which enable the connections to be made from the 10, 15, and 22 volt sources to the gate resistor itself or to the negative 5 volt low voltage connection. All of these are powered by DC to DC isolated converters, which have very, very low coupling capacitance, limiting the capacity for voltage shoot through. These all then go together to provide the driving signal to the silicon carbide MOSFET.
Marie, thank you for your time, attention, and attending my presentation today. I look forward to any questions you may have about my work.